Um, okay, so hello everyone. I'm Diego Ochoa from Power Smart Control. Today I'm going to show you how to use the Smart Control in order to design the control loops for the control loop for the three-phase two-level PFC rectifier. So, Smart Control is a tool that allows to design in an intuitive and simple way the control loop of the power electronics converter. This tool is very useful in sectors like industry or education. This smart control adapts to different levels of knowledge. There are three ways to define the converter plant. So the first way is it's called the predefined topology, in this case we can find several transfer functions like the most typical power electronic converters, like for example buck converter, boost converter, phase shift full bridge converter, dual active bridge, and the new topology that it's included in the new version of the smart control, that it is the three-phase two-level PFC rectifiers. The second way is to import the data from the TXT file. For example, if you have a PSIM simulation, you can use the AC sweep function in order to get the frequency response of the plant of your converter. In that way, in a smart control, you can import this information, this frequency response, in order to design the control loops. And the third way is to define the plant in order to use the equation editor. So perhaps to use this option, it's necessary to have some experience in converting modeling. And this option is very versatile, and you can write the transfer function of any of the power converter. Once the control loop has been designed, the result can be exported directly to the PSIM template. The control can be in the three-phase two-level PFC rectifiers. You can export the control structure in two ways. The first one, if you want to use the PSIM functional blocks, and the second one, if the control structure is implemented in a DLL block that contains, for example, a C code. Finally, Smart Control allows you to design the control loops in continuous domain or analog control, and in discrete domain or digital control. When we open the Smart Control software, the first window that appears is this Start menu. Here we have in this area, this is that we call the predefined topology. Here we have different options for the different control structure. For example, if you have a DC-DC converter, you may have some control structure, for example, single loop. If you just control the output voltage or the inductor current, or maybe you can design the control loop for the peak current mode control. Or, for example, in the DC-DC converter, if you have a double loop or average current mode control. Remember that the inner loops typically control the inductor current, and the outer loops control the output voltage, for example. In the predefined topology, we have two rectifiers. This one represents the one-phased PFC rectifiers. And the new topology is this one that represents the three-phased PFC rectifier. In this example, if we select the average current mode control, the next window that appears is this one. And this window showed the design flow of the smart control. So here we have the power stage. We can define the input voltage, output voltage, the value of the capacitance, inductance, etc. Then we have the sensor stage. Here is one for the current sensor, and we have one for the voltage sensor in this case. And this is a DC-DC converter. So after that, we have to define what type of compensator we want to tune. So in the predefined topology, we have three types of compensator: the type 2, type 3, and PI compensator. And also, you can use the equation editor to tune your own transfer function of the compensator. Here we have the solution maps that is represent the relationship between, in the x-axis, we have the crossover frequency, and the y-axis, we have the phase margin. So with the cursor in the white area, ensured that our control design will be stable. So we have one solution map for the inner current loop and one solution map for the outer loop. The second way to define the converter plant is if you are, I already mentioned that if you have a PSIM template, you can use the AC sweep function and you can import directly the frequency response to a smart control. Or if you have an experimental prototype, you can also measure this transfer function using a frequency response analyzer. Okay, so the third option, in order to define the plant of the converter, is using the generic topology or using the equation editor. In that way, you can write your own transfer function, and you can use a Laplace variable S domain in order to design analog control, or also you can define in C domain in order to tuning or design control loops in digital control, in digital domain. So another tool that Smart Control has is the parametric shift filter. This window, you can specify some range for the input parameters. For example, you can change the input voltage, the value of the inductance, and value of capacitance, etc. With the slider, you can change the value, and you can see how the results are updated automatically. Here, this is the main window of the smart control. When you are designing a control loop for DC-DC converter, for example, and here you can see the solution maps. Remember, the solution maps is the relationship between a crossover frequency versus a phase margin. So the white area is the region in where our control will be stable. So the next part, once you design your control loop, you have different options to show you that the smart control can show you the results. For example, if you have a PSIM template, your own simulation, and you just want to know what is the value of the key P and TI of the PI compensator, you can go to the output report, and you can just copy the numbers, the value of the parameters. Another option is if you don't have a PSIM simulation, Smart Control can create for you a PSIM template. In that way, we can export in two options. The first one is using the PSIM functional blocks, and the other option is to use a C code option. Also, all the transfer functions that Smart Control plot can be saved in a TXT file if you want. So in the installation folder, we can find some tutorials about how to design the control loop in the three options that I mentioned before. The first one is to use a predefined topology. That is the easiest way to design a control loop for the main topologies, most of the topologies. The second one is to using the import data from a TXT file. And the third one is using the equation editor. So here you have also an example in order to design, for example, a digital control loop. In the Smart Control Using Guide, also you can find the user manual and the what's new. This document contains all the new features that the latest version has. So a summary, here we have the links for the PDF tutorials. Also, we have some links for the video tutorials that it's related how to export or how is the connection with PSIM with smart control. So today we'll design the control loop for the 3-phase 2-level power factor corrector rectifier. So in that way, we once design the control loops, we export the templates to PSIM using PSIM functional elements or using the DLL with C code. This is our contact information and start the live demo. So in this step, I open SmartCtrl. Okay, this is the what's new in the last version of SmartCtrl. So closed. This is the start menu, and here we click on the 3-phase PFC boost converter. Move this. So the first window that appears is the single light diagram. This is one of the most important windows in this topology. So here we can configure the different type of control, modulator, lows, EMI filter, PLL, and main filter. So in the case of the modulator, we have, in this topology, we have 5 types of modulator: the PWM, the space vector modulation, discontinuous 1, discontinuous mass, and discontinuous min. We select the SVPWM. So in the control structure, we have 3 types of controls. Two in alpha beta frame and 1 in DQ frame. In alpha beta frame, we have the option to select a PI compensator or proportional resonant current compensator. And in DQ frame, we can select just the PI compensator. So first of all, we select the PI current compensator. In the low section, we can choose 3 different types of load: a simple resistor, a constant power load, or a constant current. So in this example, resistor. In the phase loop or PLL, we have 2 types of PLL. The first one is the synchronous reference frames PLL, and the second one is the quadrature signature regenerator synchronous reference phase PLL. This one is implemented when you want to detect the sequence of your grid voltage. So in this example, we select the first option. The EMI filter, later I will be explain that option. And for the main filter, we have 4 options. Maybe we have the L filter, a simple filter. We can design also for the LCL filter. And and it is well known that the LCL filter is a 3rd order function. So it's important to attenuate the resonant peak of the LCL filter in order to ensure the stability of the system. So in order to get that, there are 2 options. You can use the passive damping. For example, if you put a RC network in parallel to the capacitor, or if you prefer, you can use the active damping that is necessary to sense the current through the capacitor and is injected to the control structure. So in the first example, I select the L filter. Okay, now we can close this window. And if you click on the control icon, you can show this is the control structure of our system. So we have the outer loop control the output voltage or DC voltage. The inner loops controls the inductor currents. We have two PI compensator for the current because we have 2 currents, the D current and Q current. And here we have the axis decoupling. And this section represents the output voltage feed forward. And then we have the inverse transform in order to obtain the modulating signal in ABC coordinate. So the next step, we have to define the inputs parameters of the power stage. Here we can define the value of the grid voltage, the line frequency, the output voltage, the output power, capacitance, etc. So after do that, you can click on OK. We can close these windows. So now we are going to tune the PLL control loop. So This is in this window, you can choose two options of the alignment. So we can have alignment with the axis, or if you want to Q axis. Another thing, it's important, you have to open the solution map for the PLL with click on in this icon here. And also, you can, if you go to this option, you can see what is the transient response of the PLL here. And the last window that I recommend you to open is the body plots here. And you can click on the PLL transfer function that represent the open loop transfer function. So this transfer function contemplate the PI compensator, the plant of the PLL, and the sensor stage. So in order to tune the PI compensator, you can define directly in this in the edit box. For example, if I want to get 50 degrees, I want to get 50 degrees in phase margin and crossover frequency, for example, 200 hertz. This is one of the options that you can define the tuning the PI compensator. If you are more familiar with more comfortable with the stabilization time and damping ratio, if you go to the edit group and select this option, you can also define, for example, the stabilization time, 20 milliseconds, and for example, damping ratio of 0.7. So see, here you can see how the transient response. Another option that you can use, for example, if you want to change directly the value of the KP and TI. So go to the edit group, and here you can select the KP and TI, and you can define a new value, for example, for the KP. Click enter, and you see how the crossover frequency and the phase measure is updated. So in another option, if you want to use the solution maps, by clicking or move your cursor, you can change the crossover frequency and the phase margin. In this example, I select for this point, 100 hertz and 50 degrees for phase margin. So now it's time to define the current sensor stage. So if you go to this option, the windows that appears this one, here you have to define the sensitivity of the current transducer or gain, and here you can define the bandwidth of the current sensor. Also, you can define some signal conditioning stage. Here you can you can define another gain and another bandwidth, and it's usually in digital control that your current have to be adapted to the ADC span. So the signal conditioning is a good choice to define some gain. So in the digital control also, it's very common to use an anti-aliasing filter. This aliasing filter generally is a Salin key filter, a second order Salin key filter, and you can use, for example, the transfer function of the second order low pass filter. In this case, you can define the gain, the cutoff frequency, and the damping of the filter. So, and the last option is the unity gain feedback. This option is very useful in order to that your the control structure see the actual value of the recurrence. So this option calculate the inverse gain of the all sensor chains in order that you calculate the error with the actual values. So that means that if you power stage has a 100 amperes the current, the error will be calculated with 100 amperes. So in this example, we choose directly, for example, 0.1 of the gain and unity feedback gain. Click on OK and close this window. In the same way, we have to define the grid voltage sensor. So here you can define a gain, click on OK. And the last step for the sensor is the output voltage sensor. That is very similar to the current loop. Here you can define a gain. Maybe we can select the unity gain feedback, again 0.5. And you have also can use a signal conditioning and low pass filter. After do that, click on OK. And now we are going to the option for the modulator. In modulator window, this is the space vector modulator that use the maximum and minimum in order to calculate the 0-sequence signal. So in this window, you can define the peak value of the carrier signal. That means that this value represents that the carrier signal starts from -10 to +10 volts, for example. And then we can click on OK. The next step is going to open the inductor current compensator. In the same time, I'll open the solution maps with this option, solution maps for the current loop here. And in the body plots, I select the option, the TI represent the open loop, the frequency response of the open loop transfer function of the inductor, of the current, and the current. In this way, you can define also directly the crossover frequency at the phase margin here. Also, you can define directly the key P, the key P and TI for the PI compensator. You can go to the D group and here. And in the PI compensator, you have two forms. The typical is the standard form that you can see in this figure. And you also, if you are more comfortable to work with key I constant, also you can use the parallel form. And here you can directly use the key I constant. So another option is to use the solution maps, and here you can move the crossover frequency and phase margin, and you can see how the frequency response is updated. So in the same way, we can select with this icon the output voltage compensator window. In the same way, we can define directly the crossover frequency and phase margin, and we have also a solution maps for the output voltage loop. So here it is well known that the inner current loops is faster than the outer loop. So if we reduce the crossover frequency of the current loop, for example, you can see how the limits of the bandwidth of the output voltage or the outer loop is reduced too. So in this example, we select, for example, for the inner loop 1K and the second maybe 350 degrees, maybe like this. And here you can also, with the TV icon, you can see the frequency response of the output voltage loop. So once you already designed the control loops, the next step is export directly to the PSIM software. So in that way, before I do that, I want to show you with this icon, we have a special, we have a summary of all of the options that you selected. Here you can see the power stage, the control structure, the PLL structure, and the sensor change for the current, grid voltage, and output voltage, and also for this part represent the modulator. So now I want to export to PSIM. Select the schematic option. Here I have to write the name of the file, for example, test1, and click on open. And in this dialog, we can select the two options that I mentioned before. The first one is if you want that the control structure will be implemented in the PSIM functional block, and you can choose the C code option. In the first example, I select the first one, click on OK. And now you can see how PSIM, you can see the PSIM template. So here you can, this is all the parameters that we defined in the smart control software. And here you can see we have the power stage. We have the transfer function of the sensor stage. We have the control structure for our system, the space vector modulator, and the PLL structure. So I want to change the total time, for example, 0.12. Okay, and then I'll click on Run Simulation. So we have to wait some seconds. So now I want to show you the output voltage. So here you can see how the output voltage of the rectifier achieves the reference, the output voltage reference. Then you can see the phase current. This is the phase current. Also, I want to show you, for example, the modulating signals. That this space vector modulation is like a third harmonic injection. And also we can see the theta angle of the phase. Okay. So the second example I want to show you is that the control will be implemented in the DLL. So I put the name test 2, click on open, and now I have to select the C code option, click on OK. And as you can see here, the power stage and the sensor stage is the same as the last example, and the difference is here. So now we have a DLL that contains a C code. So if you double click in this element, you have to select use external file, and this .c is was created by the smart control. So we have to select this option, click on OK, and now you can see the C code. So you know that the part transformation contains the sine and cosine function, for example. So in order to implement in the microcontroller or microprocessor, is usually to use the lookup table. For that reason, here in this example, we already contemplate that the sine function is stored in a lookup table. In the same case for the cosine function. Also, this code has implemented the phase lookup loop, as you can see in this part. The control structure here is the outer loop and the inner loop, and you can see in this part, for example, the different equation of the PI compensator. We used the backward Euler technique in order to discretize the compensator, and also you have some algorithm for the anti-wind up algorithm. So in the last part, you can see the modulator are also implemented in C code. So in that way, I want to show you the simulation. Here we have to reduce a little bit the time step, and the total time is the same. So if I run the simulation, the simulation takes some minutes. Maybe I want to show you the output voltage here. Here you can see how the output voltage can achieve the output voltage reference. That is very similar to the last simulation because it's the same parameters. The difference is just that in this case, we use the DLL. The control structure is implemented in the DLL block. So also we can see for example, the phase currents here. That's it. Okay. So the next example I want to show you, I closed this project. Nope. And I open a new file. So another option that you can access to the three-phase two-level PFC rectifier is going to this icon here. And now I want to show you what happened with the LCL filter. So I select a LCL filter. The modulator, I select the space vector modulator. And for example, in that case, I select the alpha beta frame plus PI current compensator. So now we don't have a PLL. So if you open the power stage here and the body plots, for example, for the body plots, and I want to show you the open loop transfer function of the current plant. So here you can see the resonant peak of the LCL filter. So it's a little bit attenuated because we consider a parasitic resistance in series with the capacitor. So if I reduce this value, for example, to 1 milliohms, you can see how the peak increase. So now, and the phase drop is more abruptly. Now, we have to dump these peak resonant peaks in order to ensure stability of the system, in order to design the control loops. So if I select the passive damping, you can see how attenuate these resonant peaks. For example, if I increase a little bit the capacitor of the damping network, for example, to 4 micro, so and click on OK, you can see how the resonant peaks is attenuated. In the same way, if I select, for example, the LCL active damping, so remember, I want to show you the control loops here. This is the control structure for alpha beta control. So here we have two loops. The outer loops control the output voltage and impose the active power. This part represents a reference current generator. We have this, the difference between the Q and alpha beta frame is that the reference in alpha beta is the type, a sinusoidal type waveform. So we have the inner loops, and this is the active damping. So we sense the current through the capacitor. We multiply it by the gain KD, and then it's added to the control structure. So in that way, in the power stage window, appears the KD parameter. If you increase, for example, this number to 5, you can see how the resonant peaks is attenuated a lot, and the phase drop is smoother. So in that way, for example, I select again, maybe I close this window. I select the compensator windows, the solution map for the current, or the solution map for the output voltage again. And here we can define, for example, I select 5 kilohertz, the crossover frequency of the current loops. And maybe for the other loops, I can choose 700. Okay. So this example, I want to export to PSIM. And now I'll set the name as test number 3. Click on open and S domain block design. Okay. And here you can see this is the power stage for the LCL filter, the sensor stage, and here we have the control structure in alpha beta frame. And here you can see the active damping technique. So in this case, we sensed the current, both inductor currents, and we estimate the capacitor current with this operation. So again, we can simulate this circuit, and you can see, how the output voltage achieve the reference. And also, we can wait some seconds. And here, okay, put here and here. This is the output voltage. You can see the grid side inductor phase current, for example. And also you can see the modulating signals. So the control loops is stable. Okay, so now we can close this simulation. And the last thing that I want to show you is that you can plot in the body diagrams, you can plot different transfer function. For example, one of the complex transfer function that it's important and is the input impedance. For example, there is an analogous equivalence impedance in DQ frame. For example, the input impedance for the LCL filter in DQ frame. Remember that the input impedance in DQ frame is a matrix. You have a 4 impedance. So in Smart Control, you can plot the diagonal impedance. So that means that you can plot the input impedance for the DD or the input impedance for the QQ axis. So and I show you this. Also, you can plot the output impedance of your rectifier and the audio susceptibility here. So the last things is, if we go to the single light diagram, is related to the EMI filter. In that way, we have a 4 structure that is the most common structure that we consider. So if you select, for example, the structure 1, and you go to the EMI filter window, you can see that we have one state for common mode filter and one state for differential mode. Here you can see if you select the structure 2, for example, is the same as the structure 1, but the difference is the damping network in the differential mode. If you select, for example, structure 3, you have a 2-state for the common mode filter here, and 2-state of the differential mode. And the last structure is, for example, this one. So in that way, for example, if we select the structure 2 and open this window, we have an option that plots the attenuation of the DM filter and CM, so the differential mode and common mode. So here, this tool is very useful, for example, for preliminary designs of your EMI filter that you can check, because you can check if the attenuation, what is the attenuation at a specific frequency here. So if you change, for example, the value of the inductance of the EMI filter, the body plots are updated. And also, it is well known that the interaction between the EMI filter and the regulated converter may cause stability problems. So in that way, it's important to it's important to know the input impedance of the PFC rectifier and the output impedance of the EMI filter. So that is all. I appreciate for us attend in this webinar.